Okay, I'm going to go ahead and get started. My name is Chris Rule from the Research Division here at CARB, and I'm really happy to be here today because I get to introduce one of the best contracts I've managed here at CARB, and that's work that Tom Kirkstetter, Rob Harley, and Chelsea Preble have done measuring on-road emissions from the heavy-duty fleet, and they've done this at Caldecott Tunnel, as you'll hear about in detail coming up. Before I get started, just one logistical announcement. If we do get a fire alarm, please exit out either of these two exit doors and assemble at Cesar Chavez Park, which is cat-a-corner to this building on this intersection, just diagonally across the street. So if we do get a fire alarm, that's what we should do. Great. Okay, well, I'm going to move on then. Talk a little bit about these real-world heavy-duty emissions measurements and why that we are interested in these. And really the main reason is that we need reductions in emissions, both of NOx, nitrogen oxides, and of black carbon, or diesel particulate matter. We use black carbon as a proxy for diesel particulate matter. And there's many reasons why this is important. With NOx emissions, we have national ambient air quality standards that we need to meet. We have SIP plans that we generate to meet these. And many of these SIP plans, state implementation plans, require that we reduce NOx emissions. And NOx emissions are largely emitted by heavy-duty vehicles. They're not the only source of NOx, but they're one of the biggest sources in our inventories. And so that's the main reason that CARB has passed regulations, incentives, various actions have been taken to try to reduce NOx emissions. And we need to find out how well these regulations are working in the real world. And so that's fundamentally why we have set up this contract and had this research team from UC Berkeley measure these emissions of NOx. And this NOx is relevant, of course, both for ozone production and also for secondary PM. And there are large areas of the state, as you can see on the plot here, which are in non-compliance with both PM and with ozone standards. So we've put a lot of effort into reducing NOx, and today we'll hear about how those efforts have gone in the real world. In addition to NOx, I mentioned BC, or black carbon, as a proxy for diesel particulate matter. And this is another thing that a lot of effort at CARB has gone towards in recent years to reduce emissions of diesel PM. It's been declared a carcinogen, so the health effects of diesel PM are pretty well established. And in fact, if you look at the slide here, you can see that we can take diesel particulate matter emissions and transform that into increased cancer risk. And in this case, it's increased cancer risk based on 1 million residents. And you can see, of course, that a lot of progress has been made over the past couple decades with the introduction of DPFs and other emission controls. But the total cancer risk is still at 400 per million. And that's given all of the chemicals that I've listed up here. But you can see that diesel particulate matter is a big chunk. It's the single biggest contributor here. And so we're still talking about what we consider to be an unacceptably high level of risk due to diesel particulate matter, even though we have made a lot of progress, as you can see on this chart. And so, as you know, CARB has done a lot of things, truck and bus rule, DPF implementation, taken lots of efforts to reduce diesel particulate matter. And today we'll get to hear about how effective these have been based on real world observations. As I mentioned, we have made a lot of progress to date. The work is not finished, of course, but we do want to acknowledge that a lot of these efforts have been paying off. CARB passed the Diesel Risk Reduction Plan about 2 decades ago, which set very ambitious goals in terms of reducing diesel particulate matter emissions, 85% reduction over 20 years, basically, which is a pretty sharp decline. And actually, as we'll hear more about later, it required not just tightened certification standards, but retrofit requirements as well in order to achieve this large a reduction in BC emissions over such a short time period. And so, like I said, we'll hear more about that later on, but I just wanted to point out that, you know, we're not just talking about increasing, tightening certification standards here. We're talking about retrofits. We're talking about lots of different efforts that have gone into reducing diesel particulate matter. And of course, one other thing I wanted to mention is that recently we tightened the opacity threshold. It used to be that 30% was considered the pass-fail cutoff for field testing of opacity, and that's been recently reduced to 5%. So just another example of one of the many efforts that CARB has recently put into controlling diesel particulate matter because of its well-known health effects. So that's just the context I wanted to put in this. Obviously, we'll hear a lot more from Tom Kirkstetter in a second. The research team that we had for this project was really top-notch, I think, and it involved Tom Kirkstetter, Rob Harley, and Chelsea Preble. They'll be talking primarily about their work at the Caldecott Tunnel in Oakland today, but we've also had them do similar work at the Port of Oakland, and in fact, that's what you see a picture here from the paper that Chelsea is the first author on from the Port of Oakland. There have been several publications, as you can see here, and I don't think I even have all of them, so if I'm missing any, maybe Tom will fill us in later on, but you know, primarily what they've done so far is publish the Port of Oakland results, although that last paper from 2018 does have some of the Caldecott results. And we hope, of course, to see some additional Caldecott results in, you know, published in journals coming soon. And I'm going to wrap up with that. I'm just going to leave this slide up here. This has got some links, and of course, these slides will be on the web. So if you want to get more information about our in-use heavy-duty emissions programs, there's lots of different links on the CARB website, and here are just a few of them. I'd encourage you to check these out on your own time, but with that, I'm going to turn it over to Tom Kirkstetter, and he'll be talking about his work at the Caldecott Tunnel.
Thanks very much, Chris. Hi, everybody. Thank you for inviting us out here to give this seminar. It's a nice opportunity. Thanks for those of you who are checked in online. I understand there's about 22,000 of you. And thank you to those of you in the room. Oh, let me advance the slide. I could do that here, yes? Okay, good. So let me just start again. Chris, thank you for commenting that we are a high-performing team. We work hard to do that. I'm glad that you at least say so aloud. It's very kind of you. Let me acknowledge my co-authors and collaborators, Rob Harley, who's also a co-PI on the project, with whom I've worked with for many years, and it's really been a pleasure. And also I've worked many years with Chelsea Preble, who began this work as a graduate student and is graduated. Thank you to CARB for giving us a great research opportunity along the way, and Chelsea is now a postdoc at UC Berkeley. And really the leader of much of the field work, or all of the field work that I'll be presenting to you today. Let me also thank the California Air Resources Board for funding this work, and frankly, for funding research that I've conducted since 1993, which is just after I arrived in California. So California, as you know, is at the forefront of the nation in setting environmental regulation. From a researcher's perspective, it means there's always something interesting to address, and it's great that we have the opportunity to conduct an independent research operation and provide information about emission control technologies, but also provide information that CARB uses to understand the impacts of its regulations and emission control policies. I'd like to thank specifically Chandan Misra, who started as our program manager before moving to another section in the Air Resources Board. And Chris, thanks for continuing and working with us through budget modifications, and you were very super kind along the way. Appreciate it. I'd like to thank Jeremy Smith and Mark Berniski for participating with us in our last campaign at the Caldecott Tunnel in 2018, when they set up the peak system side by side. It meant we didn't have to set up a camera system. You did it for us. That was super helpful. And you brought Cafe Peaks, which is actually a cafe. Tony Brazil, Alicia Violet, and Mike Sutherland for providing us matched license plate information, matching our license plates to several of the state-maintained databases, which is a critical part of the work. The Bay Area Air Quality Management District, specifically Phil Martin, for providing the research van and other support to us. I'll be mentioning the research van in a few minutes. And also part of Chelsea's Part of this work was funded by a graduate fellowship for Chelsea during the earlier years. So the EPA sets emission standards for new trucks that are increasingly stringent with time. And this plot shows how the emission standards for PM and NOx have decreased many times since 1988, such that today allowable emissions are about 2% or less than they were in 1988. The most recent standards for PM and NOx required the use of diesel particle filters and selective catalytic reduction systems, respectively. I'm showing here a combination of a DPF SCR system with a decomposition reactor in between. So diesel particle filters are common, if not nearly universal, on all 2007 and newer heavy-duty diesel trucks. Of course, they're a ceramic substrate, a wall flow filter, which physically removes and traps soot particles. Those soot particles then have to be removed from the filter, which can be done either actively or passively, or a combination of the two. Passively, one approach is to convert NO to NO2. Diesel exhaust, as we've heard, is plentiful in nitrogen monoxide. So the nitrogen monoxide is converted to NO2, which then oxidizes the trapped soot and regenerates the filter. As a result of that intentional conversion of NO to NO2, however, there's some potential, and there's some evidence that you can have increased NO2 emissions from the tailpipe. The SCR system works by first injecting a urea solution, a urea water solution over a thermal decomposition reactor. And urea has two amine groups connected by a carbonyl functional group. So 1 mole of urea would yield 2 moles of ammonia. The ammonia would then react and reduce the nitrogen oxides, as shown in the second, or the bottom line equation. The performance of SCR systems depends on the dosing and the subsequent stoichiometry, as shown by the bottom equation line, which also affects the temperature of the catalyst matters. The overall system performance is also influenced by the presence of an ammonia slip catalyst at the tail end of this chemical reactor on the tailpipe of the truck. The performance affects the overall reduction in NOx, but also the potential increased emissions of nitrous oxide, as well as ammonia and isocyanic acid. So offsetting the emission benefits that occur with tightening emission standards for new trucks, of course, is increased activity, shown here in terms of increased diesel fuel consumption. So this plot shows the changes in diesel and gasoline fuel consumption relative to 1990, and this span is about equal to the span that I showed earlier for the emission regulations. So where over the same period of time when emission standards dropped by more than 98%, diesel fuel consumption doubled. Of course, that offsets the gains. To accelerate the benefit of new and more stringent emission standards for new trucks, the California Air Resources Board, as you all know, have adopted a number of regulations. So this study will focus on observations of on-road trucks, which were influenced by the Air Resources Board truck and bus regulation. And that is to accelerate the modernization of the fleet, to accelerate the penetration of the DPF and SCR technologies into the on-road truck fleet relative to what would happen without such a regulation. Our study consists of 3 different measurement campaigns at the Caldecott Tunnel. And I show you the years here is 2014, 2015, and 2018. At the time of our first campaign in 2014, engine with model years 1996 through 2006 had to be equipped with diesel particle filters, either by a retrofit or by engine replacement. And then in the subsequent campaigns, a certain portion of the fleet, first pre-1994 engines and then pre-1996 engines, had to be replaced with 2010 and newer engines. So accelerating the adoption of both DPF and SCR. And the objective of our study, to put it simply, is to quantify the emission of gaseous and particle phase pollutants from thousands of on-road in-use trucks operating under normal conditions, in this case, upon entering the Caldecott Tunnel. And we are tried to be comprehensive in the number of pollutants that we measured, including the targeted pollutants, so NOx and a proxy for diesel particle matter, black carbon. But we also measured NO2 emissions, we measured ammonia emissions, nitrous oxide emissions, and so on and so forth. And of course, part of the reason why we are measuring emissions over a period of time is also to try and evaluate the extent to which there's any evidence for deterioration or lack of performance in diesel particle filter systems, where we've seen that, for example, at the Port of Oakland. So as Chris noted, we have made measurements both at the Caldecott Tunnel and at the Port of Oakland. This study allowed us to make measurements in 2014, 15, and 18, but we also made measurements in 2010, which was before much of the influence for the truck and bus regulation. So that provides us a convenient baseline with which to compare the emissions in this study over time. We made measurements at the Port of Oakland for trucks en route to the Port of Oakland, also over 4 different years. In addition, I think, as you mentioned, Gary Bishop and the late Don Stedman and Molly Haugen have made measurements in other locations in California. So by enlisting in the universities, the Air Resources Board has assembled a wealth of information which serves as an independent investigation, independent data to evaluate the performance of emission control technologies in use, and thereby also to help evaluate the benefits of the California Air Resources Board truck and bus regulation, as well as the drayage truck rule. At the Caldecott Tunnel, at the entrance, trucks are traveling at highway speeds and up a 4% roadway grade. So the engine load is pretty high, especially compared to some of the other locations we just referred to. About a quarter of the trucks that we see entering the tunnel are also found in the drayage truck registry. But it's not just the drayage truck fleet. There's 75% of the other trucks are made up of cement mixers, dump trucks, flatbeds, heavy garbage trucks, construction equipment, and so on. So it's a pretty diverse population that would be more representative of the on-road fleet throughout the state. I'll tell you in a minute about the method by which we capture the emissions from individual trucks. And we can report emissions on a truck-by-truck basis, but what we tend to do is to categorize emissions in 2 different manners. One is we report fleet average emission rates that correspond to each calendar year when we make the measurement, so we can sort of track the fleet's emissions over time, which is very useful. But then we can also bin subpopulations of the truck into these 5 different categories, which are based upon a combination of engine model year and emission control technology. So starting with 2010 and newer engines that are equipped with both DPF and SCR, moving backwards in time to 2007, 8, and 9 engines, which are equipped with diesel particle filters at the time of manufacture. DPFs that are on older trucks, so these are trucks that are retrofitted with DPFs from 1994 to 2006. And then we also see at the tunnel, or we had observed at the tunnel during the study, a fraction of the trucks without DPFs. And we actually split those into 2 different categories, as I've shown here. Modern DPFs, the trucks with engine model years 2004 to 6 without DPFs, and then older ones. And there's a good reason to do that, because in 2004, that was when the EPA required a new, tighter standard for NOx. That was a year of a significant change in NOx emission standard for trucks. I want to get to the results because that's where things are exciting, but as an experimentalist, I also want to take the time to acknowledge how important it is to make careful measurements, especially in a study where you're comparing one year to the next to the next. You want to make sure that the changes that you're reporting are actually real and not due to different configuration of your equipment. So we've been at this for a long time. As I noted, I've been at it since 1993. And we take great pride in making sure that our measurements are robust and believable. So we tend to use high-grade equipment, the highest available to us at the time. And in this case, we're using very fast-responding sensors. Unfortunately, there are lots of really good high-grade, fast-responding sensors available. For measuring CO2, we use a Lightcore 7000, which is the best of the Lightcore models, a very robust analyzer. We measure NO and NO2 using two separate ecophysics chemiluminescent detectors. They're shown just behind Chelsea on the right-hand side of the figure. There you go. We set one to NOx-only mode and the other to NO-only mode. So we're actually measuring in 1 hertz. Actually, I think we're measuring in ½ hertz. NO separately and NOx separately. And so by difference, 2 hertz, yeah, twice as fast, right? Twice as fast. Thank you, Chelsea. We're measuring separately NOx and NO. And so by difference, get NO2. We also purchased a CAPS, an aerodyne cavity attenuated phase shift monitor, which measures NO2 directly. And in some cases, when we're measuring a pollutant in 2 different ways, it gives us the ability to compare emission factors that we measured the 2 different ways, which gives us further confidence that we're doing a good job. We measured N2O, nitrous oxide, and ammonia using Los Gatos Research and Picaro instruments, which are very nice instruments. And thank you to the Air Resources Board actually for loaning us both of those so we can do this. For particles, we measured black carbon. We've been using an ethylometer, an AE16, for a long time. And of course, along the way, McGee introduced the AE33, which is a dual spot ethylometer. The dual spot ethylometer corrects for a pretty important artifact in the measurement known as a loading artifact or a shadowing artifact. And it does that automatically by comparing sort of 2 differentially loaded filter spots. We have been using the AE16, which is not a dual spot instrument, but we've been developing our own correction scheme, being well aware of that artifact. We've published on that explicitly. And we do that by comparing the AE16's black carbon measurements to a DRI photoacoustic spectrometer, which Pat Arno made for us custom. And in fact, here I'm showing you actually the relationship between emission factors. This isn't concentration, but actually emission factors computed based upon the AE16 and the AE33. This is a scatter plot, which shows a really good correspondence, which made us feel really good about A, our correction scheme, and B, that the AE33 really works. If Tony's listening, right on. We measured PM. We focus much more on our black carbon results. In fact, I think I don't even have a PM measure here. And the reason is that we have had a very difficult time, which means we didn't satisfactorily calibrate PM based upon sort of a gravimetric mass. And the reason is that over the timescales that we're measuring emissions of trucks, we just don't collect enough on a filter to weigh it and make a good comparison between a time-averaged PM measurement with either the dust tract, which is the light scattering instruments, or a proxy for PM, or the DMM, which is apparently a more robust analyzer. But we measured particle number concentrations. We measured particle size distributions. We report on those in the final report to the Air Resources Board. I think we've published on some of those, at least for the Port of Oakland work, and there's more publications forthcoming. Okay, so this slide illustrates our plume capture and carbon balance approach or method to compute fuel-based emission factors, where we're reporting grams of pollutant emitted per kilogram of fuel burned. So the pictures illustrate the plume capture method, and as you can see, we closely align our sampling duct, which brings the air into that van with all the equipment. We closely align that to the point at which truck exhausts, or so the truck emits the truck's vertical tailpipe. As you can see here, this looks almost like an in-flight refueling. Truth be told, this picture is taken at the Port of Oakland just because we have a clear shot down at our sampling point in the Caldecott Tunnel. There's sort of like a faux grading, and you don't get such a clear photograph. But the same situation applies. And you could see that we measure the concentration time series of pollutants over time. And when a truck goes by, if we've captured the plume, if we've sampled the plume's exhaust, we see rise and fall. We see peaks in the CO2 concentration. So this shows 2 different trucks, one and then the other. Now, whether or not we see pollutant peaks depends on whether or not the truck is emitting those pollutants. So we are triggered to conduct a plume integration based upon the rise and fall of CO2, not the pollutants. So the equation shows how we go from concentrations to emission factor. So the ratio, for example, is the integrated area of the pollutant divided by the integrated area of carbon dioxide. So Matt, that would be expressed in terms of grams of pollutant emitted per gram of CO2 emitted from the truck, that ratio. So that's an emission index, if you will. We multiply by 44/12, which is the molecular weights of CO2 and carbon. And so that product of those two gives us grams of pollutant emitted per gram of carbon emitted. And then our carbon balance approach is to make the safe assumption that the vast majority of carbon emitted from a truck is emitted in the form of CO2. So we multiply by the weight fraction of carbon in the fuel, which is grams of carbon per gram or kilogram of fuel. And the product of all these things is grams of pollutant emitted per kilogram of fuel burn. And so that's our fuel-based emission factor. And just one further point, which is we can end up with slightly negative or slightly positive emission rates, depending upon how squiggly is the baseline. For example, this truck goes by, we're going to measure emission rate. We're going to quantify emission rates for this second truck. It clearly has quantifiable NOx emissions, and we might get a number that's slightly positive or slightly negative for black carbon, depending upon the stability of the baseline. So those are valid numbers, and we don't cut them out. So slightly positive, slightly negative basically tells us it's a near zero emission, but we're not dropping, for example, negative emission factors, because over time that would begin to skew our fleet average emissions. We record license plates, transcribe them, and match them to vehicle information in state-maintained databases. This is where I thanked several people at CARB earlier. We match, in this case, to the drayage truck registry, to truckers, as well as DMV databases. And that allows us to link on a truck-by-truck basis the emission factor profile, that is emission factors of many pollutants, to each individual truck that passes, and then the information about that truck, which is either the chassis model year or the engine model year, which are very tightly coupled in almost all cases, any verified DPFs that have been installed, and whether or not that truck might be exempt from the truck and bus regulation, which would be indicated in truckers. So now on to some results. What I want to show you first is the evolution of the truck fleet entering the Caldecott Tunnel, beginning in 2010. This, again, was before this particular study, but let's just treat this as part of the study. This is the baseline for comparison. And in 2010, about 15% of the fleet had DPFs. Very few, 2% had SCR systems, and the median model year was 2002. And in 4 years' time, the median model year increased by 6 years. And so there was a rather large change in the fleet between 2010 and the first year of our study, 2014. 72% of the trucks were equipped with DPFs. And though at the time that was the requirement, is for outfitting a large portion of the fleet, 1996 to 2006 engines, I believe, with DPFs, about a third of the fleet chose to adopt SCR systems already. So they were sort of ahead of the pace of the regulation at that point. And then the changes subsequently were a little bit more gradual, but by the time we finished our third campaign in 2018, about 9 out of 10 trucks were equipped with DPFs, and about 6 out of 10 trucks were equipped with selective catalytic reduction systems. In this next figure, I just show, with a little bit more detail, the makeup of the fleet in 2018. So the purple are the DPF, these are the 2010 and newer trucks, as shown on the slide. The red slice are the 7, 8, 9 engines with DPFs, and the retrofit DPFs. So the combination of the blue, the red, and the purple are about 9 out of 10 trucks. So the distribution that's shown in dark gray or black is about the 10% of the trucks, so the 1 out of 10 trucks that are not equipped with DPFs in 2018. Now, according to the rule, the truck and bus rule, you rather have an exemption or you should have a DPF. So that we see 1 out of 10 trucks that does not yet have a DPF in FY18 means that they're either exempt or they're not compliant. And we checked, according to the truckers database, we find that about half of this 10% are listed as having an exemption and the other are not. So that might suggest that about 5% of the fleet that we're observing in 2018 is not compliant at the Caldecott Tunnel. Okay, so now into some results. And the results will take a very similar form throughout the rest of the slides. I think I have like 12 or 13 slides on results. We're doing okay on time, right? Yeah, we're doing fine on time. So this shows NOx emission rate, gram per kilogram, based for 5 different engine technology categories. And the highest emissions are for the oldest class of trucks, and the lowest emissions are for the newest class of trucks. And if you compare the two, the trucks with SCR have NOx emissions that are 90% lower than pre-2004 engines, which is a rather marked reduction in NOx emissions. And the rest actually just go in order of engine age. So if I were to, for example, move the blue bar in the center to the second spot, going from right to or left to right, then this would all be in sort of an increasing age order. So NOx emissions are decreasing with increasing engine model year. But of course, the largest change is associated with moving from new trucks to new trucks with SCR systems. So emission factor for DPF, so the 2010 engine class, are a quarter of the NOx emissions from 2007, 8, and 9 engines. So that's the main story, I would say, from this figure, is that there's a 90% reduction in NOx emissions comparing pre-2004 to 2010 and newer engines. But I've also shown, just for some additional context, the NOx emission standard, where I've already converted the emission standard in grams per brake horsepower hour into grams per kilogram, assuming 175 grams per brake horsepower hour, which I think is a pretty solid conversion factor. And you could see that, expressed in those terms, the emission factor for NOx in 2010 and newer trucks is it's actually 4 times higher than the standard. But I don't want to make too much of that, because I think it's not quite kosher to compare the emission factor for the fleet at the Caldecott Tunnel, which is not exactly a fixed driving condition, but a narrow slice of a driving condition, and doesn't represent the overall drive cycle that's used to develop emission standard for trucks. This shows NOx emissions in terms of fleet average, and again, you see a decreasing NOx emission rate over time. Between 2010 and 2018, NOx emissions decreased by about 60%. Again, we saw the largest change in the fleet overall between 2010 and 2014, and you see the corresponding largest portion of the NOx reduction happening between those two periods as well. So if we look at NO2 emissions, and we compare this baseline, so trucks without DPFs, to the 2 different categories of trucks with DPFs, either retrofitted or equipped originally with DPFs, we see that NO2 emission tailpipe out increased by factors of 3 or 4. And again, that's because of the intentional conversion of NO to NO2 to regenerate the filters, the diesel particle filters. However, at this location, once you put an SCR on top of a DPF, we find that NO2 emissions are right back down, if not slightly lower than our baseline values. So we would conclude that SCRs actually completely mitigate the NO2 increase for this fleet at this location, which is good evidence that at this location, SCR systems are active and highly functional. Since DPFs were introduced simultaneously with SCR systems at this site, there's essentially no change in NO2 emissions over the course of this study. However, since NO2 is relatively constant and NOx emissions decrease, the tailpipe out NO2 to NOx emission ratio approximately doubled. Between 2010 and 2008, the NO2 to NOx emission ratio increased from about 7% to 15%. So where this might come into play is potentially mitigating ozone. Depending upon the dynamics of ozone formation throughout the state, the NO2 to NOx emission ratio might be influential in terms of the state's ability to mitigate ozone concentrations. So I want to show you a couple other nitrogen species. I'm going to show you nitrous oxide and then ammonia, just as soon as I have a sip of water. So we find that, or we measured that all categories of trucks either without a DPF or with a DPF, but without SCR systems, have essentially 0 N2O emissions. You can see our confidence intervals basically are about 0. But there's a clear emission signal so clearly trucks with SCR systems emit nitrous oxide. And you can see these vertical bars are 95% confidence intervals, so it gives you a sense of the skewed nature of the distribution. So nitrous oxide is a result of the combination of ammonia plus nitrogen dioxide. And again, there's plenty of nitrogen dioxide downstream of a DPF, which forms as an intermediate product, ammonium nitrate. And then depending upon the high temperature window, that can thermally decompose, which would yield nitrous oxide. So we see a clear signal for nitrous oxide emissions from trucks with SCR systems. Now, of course, nitrous oxide is a greenhouse gas. It has a global warming potential of about 300 on a 100-year timescale to 60 on a 20-year timescale. However, probably the main concern about increased nitrous oxide emissions is that it's an ozone-depleting substance. With the phase-out of CFCs and HFCs, nitrous oxide is becoming a more dominant player in the destruction of stratospheric ozone. This plot shows a similar trend across engine categories for ammonia emissions as we just saw for nitrous oxide emissions, with one notable exception, which is that the 95% confidence interval here is actually much larger. The width of that confidence interval is approximating almost the height of the bar itself. So the emission distribution amongst the fleet is pretty highly skewed for ammonia emissions. As a point of reference, we compare to two published studies on ammonia emissions. The first one is actually a UC Berkeley study led by Andrew Keene, who's now at Cal Poly, San Luis Obispo. And this is for emission rates of ammonia emissions for light-duty vehicles. So on average, we're finding that the fleet at the Caldecott Tunnel has an emission factor that's about half of what we saw previously for, of course, catalyst-equipped light-duty vehicles. We find that if we compare ammonia emission factor on the vertical axis versus NOx emissions on the horizontal axis, that is an inverse correlation. So almost exclusively, we find that high ammonia emissions occur when NOx emissions are low, which is suggesting perhaps that the reason for the occasional observation of high ammonia emissions is overdosing. So in a situation where you'd be overdosing with ammonia, you would almost ensure that you had low NOx emissions in a functioning SCR system. But that might tend to lead then to have ammonia as a product of this reaction. And if a truck doesn't have an ammonia slip catalyst, or if there's excess ammonia that perhaps, due to kinetics and time, can't be removed in the ammonia slip catalyst, you'll end up with tailpipe out ammonia concentrations. This figure shows the skewness of the emissions of several nitrogen species. It's a cumulative emissions distribution plot. So on the vertical axis, the y-axis, you see a fraction of total emissions in each of the species. And this is just for the 2018 fleet, so this is the most recent observation we have at the tunnel, versus a fraction of trucks ranks from dirtiest to cleanest for each pollutant. So the way you would read this, if you haven't, is, for example, we say the dirtiest 10% of the trucks are responsible for about 95% of ammonia emissions. And I've chosen to illustrate that one because that's an incredibly skewed distribution, which means that most of our observations of trucks show that trucks have very low ammonia emissions. However, about 10% of the time, they have appreciable ammonia emissions. So it's a very skewed distribution. Okay, so let me turn our attention to black carbon emissions. I have a couple of slides here. This shows the black carbon emission factor for each fleet that we measured in 2010 and on to 2018. And between that period, those 2 years, black carbon emission rate dropped 80%. So this is a larger reduction than we saw for NOx over the same period of time. But the penetration of DPFs is actually larger than the penetration of SCR systems. Again, we have 9 out of 10 trucks with DPFs. I thought it would be interesting to compare the trend in our measured black carbon emission rates with the predicted changes to the PM emission inventory for the state of California over time. And so what I'm showing here is the modeled PM emissions on the 2 scenarios from Kathy Jaw. And it shows the expected decrease in PM emissions over time for baseline conditions, that is, if the truck and bus rule didn't accelerate the modernization of the California fleet. And in red, the emission changes over time, the emission trend with the truck and bus regulation, which of course shows the reason for the truck and bus regulation, which is a vastly accelerated cleanup of the on-road fleet. And the 4 dots show the trend in measured black carbon emission rates at the Caldecott Tunnel, where I've normalized each value to the value that we measured in 2010 to compare the trend. And the trend is in remarkable agreement with the predicted trend in statewide PM emissions under the scenario where the rule is in place. One small caveat is that the emission inventory, of course, is the combination of emission factor and activity, whereas my dots on this slide are just emission factor. And we know that fuel consumption increased over these 8 years. I'm familiar with this, the national number, which increased by about, the diesel fuel consumption nationally increased about 10% over that 8-year span. I'm not familiar offhand, but I know somebody in this room knows how much California diesel fuel consumption increased in that 8-year span. But if we approximated it 10%, then you can see that that would be a slight offset to the trend that I've shown here in emission factor reduction. But nonetheless, pretty amazing agreement. Oh, I went the wrong way. Good, that threw me for a loop. So here I'm showing the black carbon emission factors as a function of the 5 engine technology categories. What's most striking is that the newest engine class, 2010 and newer, have black carbon emissions that are 97% lower than the oldest category shown here, which is for 1965 to 2003 engines, so a 97% reduction. And it's amazing how math works, because as a visual, you would doubt this, but the emissions from 2010 and newer trucks are also 81% lower than the black carbon emission rates from 2007, 8, and 9 engines. So that's about 1/5 of the height of the red bar. And that's interesting because the emission standard for those 2 different categories, the red bar, the 2007, 8, 9 engines, and the 2010 and newer engines, is the same. And yet we see that the black carbon emissions are clearly the lowest for 2010 and newer engines. And like I did for NOx here, I'm just showing you for a point of context or point of reference, the PM emission limit for 2010 and newer engines, which is actually above what we measure. So for 2010 and newer engines at the Caldecott Tunnel have PM or black carbon emission rates that are lower than the emission standard for PM emission for those classes of vehicles. This slide just takes a closer look at the black carbon emission rates for just 3 of the engine categories. These are 3 different categories of trucks that have diesel particle filters. So again, moving from left to right, it's trucks that are retrofitted with diesel particle filters, originally equipped trucks, the 7, 8, 9 engines, and then the 2010 and newer. So I'll just repeat again that the 2010 engines, newer engines, are the best performers for black carbon. The trucks, the 7, 8, 9 engines, in all of the years that we measured, this is showing 3 years, 2014, 15, and 18, the 2007, 8, 9 engines had the highest black carbon emission rates compared to the other 2 classes here as well. And interestingly, between 2014 and 2015, the black carbon emission rate for 2007, 8, and 9 engines on average increased by about 50 or 60%. And the 95% confidence interval is really wide there, showing that it's a very skewed distribution, which meant that that increase was dominated by a minority of the trucks, which was pretty good evidence, we thought at the time, that some DPFs may be deteriorating in their performance. That would be consistent with what we observed at the Port of Oakland, and that would be consistent with what Gary Bishop and team measured in the ports of Los Angeles and Long Beach, but also consistent with what they measured in the ports of Los Angeles and Long Beach. When they went back again, they found that the emission factor for that engine category returned to its relative baseline value. That is, the increase that we had observed disappeared, which would suggest that either those trucks were repaired or removed from the fleet by some means. But nonetheless, the poorest performer overall on this scale are these trucks with 7, 8, 9 engines. So I'm going to show you here a cumulative emissions distribution for black carbon. And this, again, corresponds to our final measurement in 2018. And this distribution is also highly skewed. So I've shown here a dotted line, which is the 10% dirtiest of the fleet, emits 73% of the black carbon emissions. So I mean, what that means, for example, for further cleanup is we should probably be focused on the trucks that are dominating the emissions, a small portion of the fleet that contributes to the majority of the emissions. If we take a closer look at the composition of that dirtiest 10% of the fleet, that's what we're showing on the bar graph on the right-hand side of the slide. And the most popular category of truck in that 10% is, in fact, the trucks without DPFs. So the trucks that are either exempt or non-compliant. And in that 10%, those trucks represent 5% of the overall fleet, but contribute nearly 50% of the emissions. I think this is my last graphical result. I just thought it would be interesting to compare the global warming potential, so the CO2 equivalent emissions, where we're including carbon dioxide emissions, nitrous oxide emissions, and black carbon emissions, and multiplying each by its global warming potential on a 20-year time basis, so multiplying CO2 by itself, 1. 20-year global warming potential for nitrous oxide is 268. And black carbon, and those are, well, that the N2O emission, GWP is an IPCC number. The number for black carbon is really much larger. As you know, it's a short-lived climate pollutant. And we take that number from Tammy Bond's paper in 2013, JGR, Bounding Black Carbon Study. And so what you can see is that the largest change is due to the reduction in black carbon emission rate. So despite the fact that you have an increase in nitrous oxide emissions, it's really swamped by the decrease in black carbon emissions. And I'm not sure if you can see, but we actually, here I'm expressing the CO2 equivalent emissions in terms of grams of CO2 equivalent emissions per mile driven, which means that we took our gram per kilogram emission factors and converted them to gram per mile so that we could include the effect of about a 4% fuel economy benefit associated with the introduction of SCR systems. So the CO2 bar is actually slightly lower on the newer truck category. Again, so N2O is a global warming pollutant, high global warming potential, but overall the large reduction in black carbon emissions combined with its really large global warming potential, even though it's a pretty uncertain number, suggests that the global warming potential of truck emissions has decreased as a result of these changes over time. Okay, so just a couple of summary conclusions, maybe to further elaborate on just 1 or 2 points. So as Chris noted at the start of the hour, or the start of the half hour, diesel trucks are a major source of NOx, both statewide and nationally. And we found that selective catalytic reductions reduced NOx emissions by about 90% compared to pre-2004 engines, if you compare that to the 2010 and newer engines with SCR systems. Diesel trucks are a minor source of ammonia and nitrous oxide emissions for the state of California and nationally. And SCR actually increased those emissions from approximately 0 to, say, 200 milligram per kilogram of ammonia, or about 1,000 milligram of N2O per kilogram of fuel. NOx is, of course, a precursor to ozone formation and secondary PM. Ammonia is a precursor to secondary aerosols, in particular ammonium nitrate, ammonium sulfate. So there's some concern about the increase of these co-emitted species. But if you compare the absolute changes, which I've done here, the emission factor for nitrogen oxide, NOx, decreased by about 30 grams per kilogram, which is about 150 times larger than the increase on an absolute basis in ammonia, which increased from 0 to 0.2. I think you weigh a really large reduction in NOx versus a small increase in ammonia emissions, and you probably come out way ahead of the curve in terms of impact on secondary aerosol formation. I noted that DPFs were very effective. Fleet average black carbon emissions decreased by 80% over the course of our study. If you compare The newest engines with the pre-2004 engines, we find a 97% reduction in black carbon emissions. More than half of the remaining black carbon emissions from the on-road fleet, as we observed at the Caldecott Tunnel, is due to the trucks that don't have DPFs. And again, about 10%, 1 in 10, don't have a DPF, so they're either exempt as allowable or non-compliant. Because I know the Air Resources Board is thinking about further mitigation of on-road emissions and considering an inspection and maintenance program. It might be that a technique like this for peaks, such as we're working together on that as well, is potentially useful to help identify as a screening tool the remaining high emitters, which might help the efficiency of such programs to find and target those high emitting vehicles. And then a final point, as I noted, that in terms of global warming potential, the increase in N2O emissions is really not seemingly a concern at all because the black carbon emissions were reduced to a much greater extent. And it's probably interest in stratospheric ozone depletion, which is really more of the interest, the concern about increased in N2O emissions. I think that's how I end my talk. I'd be happy to take any questions. There are 22,000 people online. One of them might have clapped.
This is Brandon Rose with CARB. I was a little bit curious. You were talking about in your basic assumption, I'm not sure I'll get this right, when you were calculating the total amount of CO2 versus that carbon, is some proportion of that carbon trapped in the filter and carbonaceous soot? Is it just a trivial amount that it really doesn't impact your ratio calculation?
Yeah, sure. The next most popular species is probably carbon monoxide. Maybe 1 or 2% of the carbon comes out of CO. I think unless you have an extraordinarily high black carbon emission rate, it's safe to neglect it.
Perfect. And then my other question, did you look at, could you tell the difference between a Navistar engine that used Super EGR technology from 2010 to 2012 versus something that had a straight SCR DPF combination?
So we do have some information depending upon the database with which we match the truck's license plate. And we have published on, actually, did we publish or did we just include in the CARB report, emissions by engine manufacturer? But we didn't find any strong trends to speak of. Chelsea adds it was a small sample size in that case when we split apart the trucks by engine manufacturer.
This is Seungju from ALB. I have a question about the ammonia emissions you presented. So I believe the 2018 campaign was the first time you measured the ammonia emissions.
That's right, yeah.
And have you got a chance to take a look at the ammonia emission factors by engine or vehicle model year? Because SCR technology introduced in 2010, and time goes on, they are just kind of better optimized and controlled better and tighter ammonia controls. I wonder if you see any emission factor changes over the year.
Right, so what we've looked at almost exclusively is what I'm showing you here. So we haven't split apart that last bar yet. Yeah. We have. Yeah. Chelsea says we have. I haven't. Chelsea has. So just for the folks online, in case that wasn't picked up, so there's no observable trend in ammonia emission versus engine model year for the 2010 and newer engines. Thank you.
Hi, this is Yitan from Research Division. I have two questions. First of all, can you go back to your NOx emission rate slide? Yes, that one. Yes, this one. For the 2010 to 2017 fleet, it seems like you have a very small standard deviation.
Yeah.
So does that mean the high NOx emission is a fleet-wide problem?
Yeah.
There's no high
right.
emitter problem.
Yes, we do have a small confidence interval, which suggests that the emissions distribution of NOx is not nearly as skewed as we've observed for other species, and I'll pull up this one here. So the cumulative distribution is also shown for NOx in dashed red on this slide. So it's not a straight line, so it's somewhat skewed, but less so compared to the other species that we measure. So it's more of a fleet-wide result than necessarily a high-emitting result. The other thing I would note, which I think is relevant to your question, is that on on this slide, oh, yeah, I'm sorry, I have something made up in my mind, but we don't see, yeah, I was thinking about this slide where I was looking at the 2010 newer trucks and not seeing any deterioration over time, but this is a black carbon specific slide, sorry.
All right, so I understand you don't have exhaust temperature measurement, but do you have any guess about that? Is it on the relatively cold condition, or it's the exhaust is relatively hot?
Well, at this tunnel, at this site, in order to get to the tunnel, you had to be on the road for some time. So you're right, we don't have engine or exhaust temperature measurements, but we expect that at this site, it's a hot, stabilized emission mode, so everything should be warmed up and hot. Yeah. So I mean, you're sort of really asking about why, if I may, I think why we have a fleet average or a category average emission rate that's about 4 times higher than the standard. Yeah, it's something that we're equally thinking about as well. On one hand, this is a high engine load operating condition, or maybe a high engine out NOx. But on the other hand, it's a place where we expect SCR systems to be operational and doing a really good job. We actually have the emission rate for NOx that we measure at this site is lower than the emission rate we measure for NOx at the Port of Oakland. And there are other indicators, for example, here that SCR-equipped engines have NO2 out, tailpipe out emissions that are sort of back to baseline values despite the intentional increase of NO to NO2, also an indication that SCR systems are working well. And then, just of course, the overall 90% reduction compared to the earlier engine class is another sign that SCR systems probably working well at this site.
And another one is more like a comment, because the current code of federal regulation requires you to treat NO as NO2 when you're calculating the mass emission rate. Did you do that, or? Okay.
Yeah. We use the molecular weight for NO2.
Okay.
Hi, Tom. Thank you for your presentation. Yanji from ARB. So do you have any explanation why the emission factor is much higher than the emission limit?
None beyond the hand-waving comments we've been having so far, except, I think I said earlier that we know that emissions vary a lot over a driving cycle. And the driving conditions at the Caldecott Tunnel site, it's not like they're perfectly constrained, but it's probably a small portion of the driving conditions that you would experience in a full driving cycle, and that's how the certification levels are set, sort of a drive cycle average value. So I think there's some caveat, which is what I mentioned earlier, that we're not comparing apples to apples in this situation. Where I think it's safer and best to understand how at a given place, emissions change over time. That's why we look at fleet average emission changes over time. Or at a given place, how different portions of the fleet, for example, as shown here, behave.
Thank you.
Yeah, you're welcome. Thanks.
Hey, thanks, Tom. This is Dong Min from research. I know the VOC measurement is not part of this project. And do you have a sense that how the VOC, SVOC change?
No, I'm
because
sorry.
of the introduction.
We didn't do VOC measurements at this site, so I don't have any information about it to report on.
We've got a couple questions online, so I will read those next. From Lou Browning. You make a comparison with nitrous oxide versus BC effects of SCR For a 20-year, I believe that said global warming potential. What happens when you consider a 100-year global warming potential? So how would changing the time horizon affect the conclusions, if at all?
Yeah, the overall conclusion is the same, though the difference is not quite as dramatic, but still dramatic.
And one more question from Christopher Weaver. How does your sample break down between California registered and out-of-state registered trucks? Out-of-state trucks were exempt from the fleet rules. Are there differences in higher emitter frequency between those?
At the Caldecott Tunnel site, I think we see almost exclusively in-state trucks. That's a better answer. So we get most of the matches in-state trucks, which means though that the data we're showing are for the fleet that have been matched. Those are also the same. Yeah. So I'll restate that. So if we look at the fleet average emission rate for all the trucks that we observe, which would include trucks that aren't matched in a database, which could then include out-of-state trucks, that fleet average is very much the same as the fleet average we compute, where we exclude that fleet average only to the trucks that are matched in California's databases, which would suggest that there's an influence. If the former category includes out-of-state trucks, it doesn't influence, to a large extent, the fleet average emission rate.
Here's a comment from Paul Jacobs. Dr. Kirkstetter, as a 30-year ARB enforcement veteran and now as the Energy Commission Enforcement Director, thank you for the great presentation today validating the effectiveness of DPFs and SCR on heavy-duty diesel engines. Your work and that of your colleagues is much appreciated by the 40 million breathers in California and the 325 million in the United States. So how about that? No question, just a nice comment.
Thank you very much.
And then
have coffee the next time you're at LBL.
And then a follow-up, actually. Just a point from Lou Browning that I think at Caldecott the trucks are driving uphill and therefore would have higher NOx. And I think, Tom, you mentioned this. You expect higher engine out NOx, but also warmer SCR. So it's a tricky question. Well, am I putting words in your mouth?
No, that's what I said earlier. And thank you. And thanks for the point, of course, from the online folks.
Tom, a two-point question. You are calculating fleet average emission factors rather than calculating an activity balanced. So if you see the same truck 10 times, do you take one emission factor for it, or is this?
We see some trucks more than once, but it's a small portion of the fleet that we measure more than once. Some trucks we see 2 or 3 times. I could have to look to Chelsea to tell me how we computed fleet average emission rates, but I can tell you that the number of repeats is large enough that we have an interesting data set of repeat observations, but it's small enough that it just doesn't influence our fleet average emission factor.
So you're just using one emission factor per vehicle to calculate your fleet average emission factor?
No, I think it's observations. It's an observation-based emission rate.
It is observation basis. Okay.
Yeah. But I hope my answer does make sense to what I just said. That is.
It makes sense, but it is not a fleet average, then it is what you're seeing at that site, right? It is.
Yes, but what I'm suggesting to you is I think if we averaged the replicate values and counted it once in the fleet average, we'd end up with the same fleet average emission rate, just because they're small enough a number in the population of overall observations.
It depends if the entire fleet you see, if you see the same number of repeats for it can change your calculation a little bit. The second question is, have you considered, all these calculations are based on measurement at one location, and you rightly mentioned that it is 4%, the operational characteristics are limited. Have you thought about maybe following like a peak system at, for the same fleet before or after the location to see if the different operational characteristics are going to change anything for you?
Yes, we have thought about that. We haven't done it, but I believe Chris gave Jeremy, who gave a presentation recently which summarized the emission trends? It's Chris at CRC last week, 2 weeks ago, a month ago? A couple weeks ago. That was in the San Diego, not the MSAT, Long Beach. Yeah. So Chris gave a nice presentation that summarized the results that we've observed and the results that Bishop has observed. And these are very different driving conditions. And the absolute values of the emission rates are actually markedly different. But when you focus on the trends over time, they line up really well. Again, this is just evidence that emissions vary with driving cycle. And so it's safest to sort of compare trends over time at a particular location than to compare sort of one site to another and try to compare them on the same playing field.
Couple more questions from online. Apologize, this one doesn't have a name though, but I'll read it anyway. The anomalous increase in BC measured in 07 to 09 trucks in 2014 and 2015 was attributed to a potential loss in efficacy of DPF equipment. Is it possible that it could have also been due to the deletion of DPF equipment on vehicles originally equipped, and the disappearance of this anomaly in 2018 is due to the decreased inventory of these model years of vehicles per the engine replacement or retirement of those model years, irrespective of retrofit? And so that's one question. And finally, have you measured a loss in efficacy of 2010 to 11 model year DPFs, measured 8 to 9 years later in 2018?
Well, I'll start with the latter because I'm not sure I followed the full question, the former. But I believe I'm showing here the answer to the latter question, which is that the 2010 and newer engines, the black carbon emission rate from 2014 to 15 to 16, I'm sorry, to 18 doesn't show any indication of an increasing value. So there's no evidence in this data set of deterioration of performance of DPFs on 2010 and newer engines. Now, it may be, for example, that the engine tuning, which would be different on the 2010 and newer trucks compared to the 7, 8, and 9s. The 2010 and newer trucks might be tuned for a higher engine out NOx, lower engine out PM. Maybe there's less wear and tear on those DPF systems. They have to have less active regenerations, which is less stressful and will maybe lead to less failure. That could be one of the reasons why the 7, 8, 9 engine DPFs don't perform as well. The filters themselves are sort of more burdened than the 7, 8, 9 engines, where the engine tuning there, because they're not SCR-equipped, would be attuned for a higher PM out, lower NOx engine out. And of course, there's always that trade-off.
Another question, actually, same questioner as previous. Some type of trucks are barred from driving through the Caldecott Tunnel during the day due to an explosion from a fuel tanker truck that occurred in the early 80s. If you only take measurements during the day, isn't it possible that your data does not include entire categories of trucks, such as tankers, that are barred by regulation from entering the tunnel during the day?
Sure. Yeah.
Here's a question from Brad Edgar. Can you comment on how...
Can't take Brad's question.
Sorry, I already started. Can you comment on how portable emissions measurement system, or PEMS equipment, might be used to validate your measurements? I know CARB is conducting PEMS testing of individual vehicles. It would be nice to compare a PEMS measurement to your measurement to see if there is agreement, or if there's a way to validate some of your assumptions, and to differentiate the real fuel economy of the various model years of the vehicles. Have you considered a research program to combine these two measurement techniques?
Well, the only assumption we make that's worthy of mention, I think, in this context, is what is the brake-specific fuel consumption? And there's a lot of data that show how brake-specific fuel consumption doesn't vary much with horsepower until you get to really low horsepower bins, and then it starts to increase. Over a wide range of horsepower conditions, or therefore a wide range of driving conditions, the brake-specific fuel consumption varies by 20 or 30%. It's not a large variability. So if you take a number that's smack in the middle of that, that's pretty small potential error that we could go from converting, say, a gram per kilogram emission factor into a gram per brake horsepower hour emission factor. But I'm not concerned about validating any assumptions. I'm not necessarily concerned about verifying the measurements we make because we take great care to make sure that the systems we have are calibrated. And in fact, we've even calculated the precision of the plume capture method, which is pretty narrow, especially compared to the range of variability we see in measured emission rates. The interesting part would be to further investigate some of the things we've been discussing here so far, which would be to further investigate emissions varying over a driving cycle. And so there, a PEMS system is a great thing to do. And I know that, I know that Brad and company have a light-duty PEMS, and they have a lot of interesting data. And of course, I know that the Air Resources Board conducts drive cycle analysis of the heavy-duty chassis dyno, as well as having a PEM system as well. So I think there's probably a good amount of data already in existence. I would love to actually analyze some of that data. And it might be that more of that information is warranted, in which case we could conduct additional studies, as you actually asked if we thought about doing. And I was actually thinking about my conversation with Brad at the time, and then Brad called in. So this is something that could be done to further investigate emissions over drive cycle. Yeah. Sorry, I think I belabored that. That was a long response.
So I have one more question online, and this would be a good one to end on, although if anyone has any last minutes, that's fine. Anyway, this question is from Stacy Davis. What suggestions might you offer to CARB or other regulators seeking to find and retrofit the fraction of non-exempt, non-compliant trucks without DPFs?
So what would be my recommendation to find and to fix them?
To find and retrofit these non-exempt, non-compliant trucks that don't have DPFs.
Well, I think that we and others doing similar work have illustrated that these measurement approaches can be an effective way to find the fraction of the fleet that's high emitters. And of course, we can identify the trucks via their license plates. And so that points us in the direction of using a system like ours, or maybe a more automated version of a system like this, and deploying it at selected locations around the state. This also, I think, enters into the discussion of AB 617, where we're looking to identify high-emitting sources, particularly in environmental justice environments, neighborhoods, and then mitigate those emissions. And I think that it would be a wonderful thing if we could actually identify high-emitting trucks, have some process by which we can identify or communicate with them, have a retrofit or a mitigation measure, perhaps funded by AB 6117 resources if they exist, and then measure them again, and then you can quantify the emission reductions for the dollar investment.
Okay, any last minute questions? Well, if not, I'd like to thank Tom and Chelsea for making it out here, and Rob Harley as well. It was a good presentation. We really appreciate your efforts. Thank you.
It's a pleasure. Thanks, everybody. Thanks, everybody online.